Prabha. Digital India.
Okay, can get started, I think. So now we look at the concept of equivalent SDOFs or SDOF representation. For instance, if you took, let's take a simple beam, and it's also simply supported. So clearly the weight is going to be your mass density multiplied by your volume, BD and L. Let's say it's rectangular, D and L. So and we just simply represent this as a line and say this is, especially if it is got a distributed loading, you say this is the deflection, and then the deflection, as we all know, is 5 by 384 EI by, I'm sorry, WL4 by EI. So this is WL power 4 by EI. So from here you can further say this is 5 by 384 WL times L cubed by EI. And when we talk of an equivalent SDOF, so we are looking to represent two things: the displacement of the system, and then there is the mass. So we have KEQ, and this is the load P, MEQ. What we have this is a distributed mass, but in a equivalent SDOF system representation, this mass is a concentrated mass. So we have to make some adjustments for that as well. So so this is WL. So from here we know that if you represent this as equal to P equal to K delta, you have your K equal to 384 EI by L cubed, and this is your P. And we've seen before, K depends on boundary conditions, material, your span, your geometry, as well as the type of loading. So given all of that, the curve, when you're drawing the, or when you're writing the, and you can put this even in terms of your resistance factors. So this is equal to, I'll be doing those, using those equivalent, those nonlinear elastoplastic systems in this example after we finish this topic. So if this is equal to P of T, this is the standard or the original ODE. Now in reality, when we come over here, or when we, not reality, this is reality, when we come over for modeling purposes, we now have M equivalent X double dot plus your K here and K equivalent, and then X is equal to P equivalent. Even the load itself has changed. Now these equivalencies, so we will start with here, we can and combining these two, let us say the equivalent system is Km multiplied by m x double dot plus your stiffness equivalence Kk multiplied by x is equal to the load equivalent multiplied by P. Bless you. So, here we have Km is the mass equivalence factor, the term Kk is your stiffness equivalence factor. So, in this example the stiffness the stiffness equivalence is 384. Suppose 384 by 5, I forgot that. And then you have your load equivalent, KL is the load equivalence, because now we are representing, this is representing, or this factor for example is accounts for distributed loading, different types of distributed loading. In the program for nonlinear, it accounts, this is the program says this is a concentrated load, concentrated mass. So, now we make a little change here, divide all of it by KL and here KL. Here P is a function of time. The reason we do that is to get the use, so divide throughout by KL to use the actual loading history. That is the main purpose. So, when you even use nonlinear, you can actually give a P versus T curve from your experiments. So, if you are doing experimental simulations, I think several of you are working on experimental works. Once you finish your experimental work, then you want to do numerical simulations, you have your blast pressure versus time history curves. You can use those curves directly without any scaling. So, for that purpose, and still go ahead and use nonlinear or other SDOF programs. So, you get K load mass factor x double dot plus Kk by Kl x is equal to P of T. So, and we will upload these files as well separately. So, there is a whole lot of equivalent SDOF factors. This is a lot of our work is legacy. So, you see any book, they will probably use the Biggs book. 1964 tables are still used very extensively even in the field. Consulting companies use this all the time. You can Google the book and I think you may be able to find it. So, what they have here is the loading diagram and two things to be observed. So, this is uniformly distributed load, if you see, for central point load, uniformly distributed load, and then here you have of course the mass is uniformly distributed mass. Central point mass is we will not consider that, but there are two things that you should look at, elastic and plastic. So, the load factor KL 0.64, Km 0.5 for, and you see the distribution of the elastic mass factor, the load factor in the plastic range. So, when we are talking out, for example, the elastic plastic range, P versus delta. So, we are talking in this range elastic, and we are talking in this range. They are not the same. How does this come about? You calculate your deflections, for example, and then you compare the two. The stiffnesses in particular. This, let us say, came about, where's your stiffness, load factor, then there is a load. Yeah, the stiffness, if you see plastic deformation, in this case is 0, the stiffness. And we will talk about this resistance a little bit later. What this is Rm. Now, the load mass factor is nothing but KLM. So, here you have the load mass factor KLM, and then this is KK by KL. And then you set up your differential equations based on these two factors. You have KK and you have KL. So, these are the stiffnesses in the two the other there are other will address. These are the ultimate shear stress or the shear force, support shear stress, support shear is, notice in this case we will address all of this. The support shear is in terms of the resistance, not the applied load, because we are going to the extreme situation. So, in the extreme situation it's in terms of the resistance, and then the dynamic reactions. This is more interesting. In the dynamic reactions you are talking of is R dynamic. So, for R dynamic, this is a function of the resistance curve, the resistance function that we talked about, and the loading curve. So, this is, you can say, 0.39 R of t plus 0.11 F of t. And of course, you need to find out where it is the maximum resistance, this is the maximum load. So, you have that for central point load. Other clearly you can see that in the mass distribution is 1. Here you do not need any adjustments. So, this is 1, but your the load factor is 1 because it is right there. Then the mass distribution is again uniformly distributed mass. So, that should be, it is 0.49 and 0.33, 0.5. Load mass factors are given, and the dynamic distribution is, again notice it is different. We will not again look at how they are derived. Other common scenario is a 2-point. Things you can focus on is the elastic plastic here, then the mass of the mass distributions and the stiffness distributions is right here. Maximum shear is given and the shear function is right there. Any questions? May expect, I mean, perhaps could expect one question here. If you can think of a question, what would you think of? No, we haven't done that yet. We are just going to start that. So, yeah. So, this is still using the charts. We haven't used, I have introduced a chart, but I haven't used it in an example yet. So, one thing you could think of is, should you do both an elastic analysis and a plastic analysis? You can take the average stiffness equal to K L elastic plus KL plastic. All these, as an engineer, you have a lot of leeway to work with different assumptions, and a reasonable assumption to do just one analysis to consider the stiffness is take the average of the two. Is it accurate? No. But does it work for design purposes? Perhaps. Then the next concept is, any questions again? So they have a small corrections here, incorrectly given in bigs as point. They have it somewhere here. A and B I saw. It's right here as 0.52 and 0.6. Anyway, it's not very different.
Sir, all the loading thickness is 0 in plastic.
Yeah. Not. So all the loadings you've seen, the stiffness is 0. The reason is they are assuming the loading curve to be rigid, or the resistance function to be like this. So you have your equivalent K here, P versus delta. Here the slope is 0, right? So that's the reason why they do that. If you and for other curves, it is hard to come up with numbers like this. If I change the shape of that green curve, these numbers are going to be, then is it K1, K2, then you have to set up all of that and find equivalencies. I don't know if they've done that in bigs, probably not. So this is where we start off. How, so the question is, how are resistance functions established? Truly speaking, they should be tested. If you have a material, structural, boundary conditions also play a role in it. The same material, same geometry, if the spans are different, the resistance functions are going to be different. Yes, specific not only to a structure but to a configuration as well. Suppose you take an alloy and you're developing a resistance function. It depends on the two materials, the thickness of the materials that you use. So if you change the thickness of copper and whatever aluminum alloys, then keep them as two separate materials, then your resistance function will change. So ideally you have to develop from experiments, or you can use theories to develop and then assume it is rigid plastic or estimate a K value that sounds right. More often than not, the peak value is the most, not P naught, RM here, the peak value is the most important one. What is the capacity of that section? And as you will see when we jump into concrete, that distinction is really difficult because most of it, the estimates are based on strength design. Yes. Yeah. No, it's a resistance function. So in this case, the resistance function would be R is equal to K equivalent multiplied by X for, this is, let's call it X sub E, is equal to, and let's say this is X sub M, is equal to Rm for X greater than X sub E. So the function would look and is equal to 0 for X greater than, no, X E less than X M. So, this is x greater than xm. So, your stiffness really is not coming into play when you put a resistance function there. Now, so let us look at representation of the resistance function. Or what is a resistance function? Now, two quantities that are important are in any beam loading. So, you have typically you may have a max shear here, and here you will have a max moment. And the max shear, let us say this is V max is the capacity, not the applied load, capacity of the section, shear capacity of the section. So, that is a shear capacity of the section. The moment capacity of the section, let us say, is M max. Again, it is not the applied max moment, but the capacity of the section. So, for example, we know that if you have a distributed load, the moment diagram is going to be WL square over 8 is M max, and here when we put an equivalence to it, that is so the actual moment is WL square by 8, but when we represent this, it is not exactly like a point load. The representation of the max resistance Rm, no. So, the max resistance Rm is in this case M max we say is WL times L over 8, and that WL is Rm. So, Rm is, for a simply supported case, 8 M max divided by L. This is the flexural resistance. And the shear resistance is, we assume this is Rm, this is Rm over 2. So, the shear resistance is Rm, and then consider the lesser of the two resistances. What is an SDOF system not, or same question put two different ways. The SDOF system represents which response? Between these two, flexural or shear, it represents which response? The flexure response, right? So, it represents the bending response. it is not representing a shear response. Always keep this in mind. This is things that we don't, or we assume about, this is that I talked about. You have to keep this in mind, because we never talk much about it, once or twice and then forget about it, but plays a very important. SDO of systems typically do not include the shear resistance / response, and so see if you can avoid a shear failure. What are one of the limitations? If somebody asks you and you are doing a lot of SDO of analysis and they notice that your shear response is often dominating and you are doing SDO of analysis, immediately your work is killed. Nobody is going to accept that, because no way you are representing reality. So how do you do that? Detailing in concrete. Steel, often you don't have a shear as an issue. So concrete detailing plays a very important, masonry also detailing plays an important, reinforced masonry using things like that to avoid increasing depth and other such whatever tools you have to increase your shear resistance. If you want to start looking at shear responses, and like columns for example could have large shears under blast loading. Even though you are designing your column for a bending and an axial force, are you designing a column? Do you ever design a column for shear in a building? No, right? I've never designed a column to include shear, because wind shears are quite low. The ties take care of it, and unless it is seismic, even in seismic you do have shear diagrams, but those shears are still way under capacities. So, but in blast, the same building now starts getting governed by shear. So, that is a problem. And as an engineer, if you are designing a building, then shear resistance. So, in any building or any structure design, pay particular attention to over design for shear, and that is why dynamic reactions. What is the shear? Dynamic reactions comes into play. For dynamic reactions, peak values. People might actually plot in an SDF system, or you can plot if you have R as a function of time and P as a function of time. You see this dynamic reaction here. Pay attention to this. Again, the course does not have enough time to address each one of these sort of dig further down into each one of these topics. Ideally in tutorials we would go into some of these, but at least it will give you a flavor of these concepts that we typically do not pay attention to so much in a normal design. Other examples, the second case is if you have P and we know the moment is PL by 4, right. So, in this case RM is simply 4 m max divided by L. Or the third scenario we saw was, why are these the most common ones? If you see in roof structures, you will have beams and girders, or floor structures, you will have beams and girders. And quite often for the span, for example, if it's a 30 feet span, we might put 2 beams. So these are very common scenarios, but you can clearly extend it to other cases. So based on the moment in this scenario, Rm equal to 6 m max divided by L. So there is another insert, but I won't insert it here. We will upload it. So what we have here is, I think I've showed you this one, equivalent Km. I don't know if it is. Let me see what this is. Yeah. So what I showed you is for a simply supported. Now this is a propped cantilever, and the factors are given. You see the support shears, stiffnesses, and for the 4 scenarios, typically those are the 4 scenarios. And so that's a propped cantilever, equivalent Km for simply supported, and the other one I have is for fixed, the same things again. Okay. So let's take up at least one example today. Let me make sure I've looked at everything that has that I had planned for. Okay. So we had this discussion, and I'm presenting in the system that I'm most comfortable with, but it shouldn't be. If you have any questions and as to what I'm doing, do ask. But the process is very similar. I've seen British codes. I haven't seen Canadian, and it's been a while since I've seen IS 456. So, but the procedures to calculate are slightly different, but process is still the same. So, but please do ask any questions you have. So let's take up an example. It's a 3-story structure. And the height per floor is 13 feet, 39, what it would be approximately 13 by 3 is 4 meters. What's a typical floor height here? 4 meters or 3 meters? 3 meters? Yeah, 3.6. So that's probably 13 feet, right? We'll do this problem in units, to be consistent, kips and inches. It's a 3 bay by 3 bay system. Bay is 30 feet, 10 meters. So bay width is 30 feet by 30 feet. Let's say 10 meter by 10 meters. The wall is an exterior infill wall. Tomorrow I'll take up, I don't know, I have 2 examples planned. I don't know how far we get. There's another example I've planned by using analytical methods. This is for SDOF setup. The other, I have that problem. I'm trying to convert that to the analytical to this example. I have it for a different numbers, but I'm trying to see if I can. Otherwise, I'll present it for those numbers. So here you have an exterior infill wall is basically, as we have seen, this is your column and your beam, and this is the infill wall. The exterior infill wall is a one-way slab system. So it's not your brick wall per se. Or you could even think of this similar to an exterior cantilever compound wall. That's same analogy. I've given for propped cantilevers. You can do the same thing even for if you have a cantilever. What's your RM going to be? Anybody? In terms of Mmax. Two Mmax by L, right? So what's your moment here? WL square by 2. So if it is a cantilever wall, you would take RM as 2 Mmax by L. So this is a one-way slab system. So it is and supported here and here. Bottom and the top. So what is a one-way slab system? You take this, say this span is whatever, and this is the width. If your span is more than twice this width, it's going to behave like this. So it's real beam, bending like a beam. But if this span is roughly equal or less than 2, now what's going to behave? It's going to behave like a, supported on all 4 sides. It's going to have, it's not a simply support beam structure. That's a one-way and a two-way system. So basically your load is going to the 2 side beams alone. These beams, even if they exist, are taking minimal load. No, so this is supported between the top and the bottom beams. That's why I have specified it. If you support it from 30 feet, now that's, you don't want to do that. WL square by 8 is, L is 30 feet, 13 feet. So 13 square versus 30 square. So if you are constructing a wall, it's better to support it at the top and the bottom. So one-way slab system, this is 13 feet and it's a truck bomb, and say W equal to 1,000 pounds, R is equal to 150 feet, and I know if you're mechanical, it's going to be, you have not perhaps seen this, but try to follow as best as you can. I'll outline each and every step. So the wall details, walls are typically reinforced. You can reinforce anyway, but a wall like this is typically reinforced, especially if it is bending. So this is 1.5 inches and here this is a clear of this is 8 inches and this is 1.5 inches, and these bars are what are known as number 4 at, I'll explain what that is, 6 inches center to center. A number 4 is nothing but a 4 by 8 inch or a half inch, here what we call 12 mm. I don't know if you have, is that the 12 mm bars? So 10, 12, it's a 12 mm bar at 6 inches or 15 centimeters center to center. So this is 12 mm at 150 mm center to center. And PR is applied this way. Question is the wall adequate? Tomorrow and Wednesday we'll see some very interesting ways to design. They've again borrowed some concepts, and not all companies may use it. I've seen some companies use this process, others not, but I thought this is a very creative way of doing some things, so I'll present. That's what I'm presenting. So part of it. So the first step is your blast parameters. And what we have here is, it's a truck bomb. So hence it is a surface blast. And then you go figure 2-15 from the UFC. So Z is R by cube root of W, which is 150 feet by cube root of, the data, I think I've had the data, 150, yeah. So R is cube root, weight is 1000 pounds. So this is 15 feet. So from UFC you can get the following data. So the data is PI is 4.7 psi, PR is 10.5, arrival time, we don't need this, is 82.2 milliseconds, TD is 22 milliseconds, and IR is 115.3 psi milliseconds. You'll see we do not know the type of loading at this point. Loading regime at this point we do not know. What I mean here is we do not know if it is impulsive, quasi-static or dynamic. We'll check that later. Sometimes we have to assume and then proceed with it in certain analytical situations. So that's our first step. Second step is to calculate the member resistance, and here you can use the IS. So you should use the IS 456 provisions and methodology that you have learned. I'm working with the US system. again, ask me any questions at any point. I'd like you to understand it's not very different. It's not different from different places. It's just a few coefficients that are different. The equations are very similar. So consider 1 feet width of the wall. So B is equal to 12 inches. So start with the net force on the wall. Now the wall again is this way. So we are considering the wall supported. Now you might say the pressures are different from the top and the bottom. That's fine, but design wise we assume the pressures to be uniform. So the net force on the wall P naught is PR multiplied by 13 feet multiplied by 1. So this is 10.5 psi multiplied by 13 times 12 times. So divided by 1000 comes to 19.656 kips. So remember the ratio P naught by RM. So this is where P naught comes into picture. Then second is we're doing calculate RM. We start with the strength increase factors, strength, or we'll call it strength increase and the dynamic increase factors. So here for concrete, typically we use FC, we call it FC prime, which is nothing but FCK here, which is 4 KSI, which is probably a 30 MPa M30, equivalent to M30. So the increase factors you can use the same. The SIF for 4 KSI, the SIF is 1.1 at 28 days. There was a chart I had given you a while ago which showed 3 different graphs showing the dynamic strength increase factors. So you can use that. If it is longer, typically it might even be longer than 28 days. For steel, which is our 60 KSI, so this is your 415 megapascal steel. The strength increase factor is also 1.1. Then the dynamic increase factor, this is DIF. So DIF for concrete is 1.19 and the DIF for reinforcement is 1.17 in flexure. If it is shear, that would be different. So what we get here is FC dynamic is SIF multiplied by DIF multiplied by FC prime, so which is 1.1, 1.19 multiplied by 4. So you are actually looking at a 25% plus increase in the actual capacity. And Fy dynamic is again your SIF multiplied by DIF multiplied by Fy. So, it is 1.1 multiplied by 1.17 multiplied by 60. So, this is 77 point. So, you can correspondingly use your MPAs. Yes. SIFs is, so you have a standard, right? Usually standards are minimum standards. So, that is why when you test steel, you will actually get more out of it, which is why, anybody worked in pre-stressed concrete? No? Nobody has worked in it? So, if you look at all the lot of bridges, what do you call high-rise buildings, many floor slab systems, bridges especially, girders, they are all pre-stressed, right? If you are aware of that? So, anyway, if you've done, anybody done courses in pre-stressed concrete? A few of you, right? So, when you design, when you do the actual construction and erection, usually the plant where these girders are manufactured in a plant and brought to a site, and you would have seen it, right? On all these pillars, they are coming and putting some big girders. They will actually test it locally. So, they will have, they'll have these huge, what do you call, bundles of pre-stressed concrete, pre-stressed steeling wires, 7-wire systems, and each one will have a test data which shows what the actual modulus is. Steel modulus is 29,000 KSI, it could be 29,332, or Fy is, if it is a 60 KSI or 100 KSI, what 101, 103, they go actually, because in pre-stressed concrete, when you stretch it, you need to exactly figure, it's an elastic structure. When you design pre-stressed concrete for blast applications, you can use your elastic to a large extent. You have to use the plastic too, but for predicting a normal behavior, you can even design it for a lower LOP and see if it works. There, actual deflections are elastic. So, you need exact E value, and to predict the limit, you need exact Fy values. So, they actually test it. Normal concrete, you never do that, or normal steel, you assume you always will get more if you test it. It's a little aside, but something to keep in mind. Then, so once we have the strength increase factors, the moment capacity of the section, and if you are not steel or concrete, if you are other branches in engineering, or if you have forgotten, you can use these expressions if we have a tutorial. So, the moment capacity of the wall is given by the following expression: M max is the area of steel multiplied by the Fy dynamic, basically the force multiplied by the effective depth. This is the effective depth. This is to the depth from the compression to the center of the steel. So, here we have the steel total depth is 8 inches. This is H, effective depth is D. This is the compression side, and this is the tension side. Remember that we assume that anything below this tension concrete does not exist, right. So, so on the tension side, that is D, and the compression block, again I know it might be a challenge for mechanical. So, this is the compression block. Here We use 0.85 C prime. You would be using something different. But anyway, this is D minus A over 2. This is A. Just assume that A is the depth of the compression block. Anything below that, above that red, that concrete literally does not exist. So, several things to calculate out here. Now, D can be taken to be the total depth minus the 1.5 inches. This is 1 point, clear cover is 1.5 inches, minus the diameter of the bar divided by 2. So, in this case, this is 8 minus 1.5. Bar diameter is 0.5 inches. It is a number 4 bar or 4 by 8. So, the effective depth comes to 6.25. Then the depth of the compression block A is given as, from force equilibrium, AS multiplied by Fy dynamic divided by, again do not worry about, this is what we call the Whitney stress block. I don't, you might be using the same thing, multiplied by B, but use this expression. Now, AS is its number 4 bars at 6 inches center to center. So, basically this is 2 bars per foot, or AS can be taken to be 0.2 square inches is the area per bar, cross section area per bar multiplied by 2. So, AS is 0.4 square inches. So, A comes to 0.4, the FC prime dynamics, sorry. No, AS Fy, that is Fy. So, 77.22, so that is a total force out there, 0.85 FC prime, this is also dynamic. So, 5.24 multiplied by 12. So, this is 0.58 inches. So, Mn is AS Fy dynamic multiplied by D minus A by 2. So, this is, now again this is per foot width. We are taking 1 feet wide wall. So, 0.4 multiplied by 77.22 KSI multiplied by 6.25 minus 0.8 is. So, this comes to 184 kip inches. Process is same, right, to calculate Mn here also, more or less. You use the Whitney block here also. Oh, so there is another way to calculate the compression force. Provisions are a little different. Coefficients are different. Coefficients are different. So, Whitney block for us, that 0.85 is the coefficient to convert that non-linear concrete to a rectangular block. What's that? Parabolic. We also use a parabolic, but the parabolic region has been converted to a rectangular, equivalent rectangular block. That is why I am able to use D minus A by 2. You see that A by 2? So, that is because the rectangular block depth is half. So, the moment arm is D minus A by 2. Oh, triangular, I see. Oh, parabolic, okay. So the we call it the Whitney stress block. Anyway, you can calculate your moments by IS, the procedures that are adopted here. So it's a simply supported wall. So therefore, Rm is equal to 8 Mn divided by, notice the phi is 1. So this comes to 8 times 184 kip inches divided by, sorry, L, not. So this is 13. So what get here is Rm is equal to then the member resistance in shear let me make sure I'll finish this problem. We have about 15 minutes. I think I can get it done. Ooh, 5 pages. Okay. So the member resistance in shear, again these are ACI 318 code provisions. FC prime dynamic is now SIF multiplied by DIF multiplied by FC. Now in shear, the SIF is still considered, but the DIF is 1.0. In shear, it's a very brittle failure. So note that the dynamic increase factor is 1.0 multiplied by 4 KSI. So this is the shear capacity. This is the concrete. In fact, now equations have changed. We now have, I don't know if it's an advanced idea, but what are known as the L by D ratios or deep slab, those kinds of things. Shear fracture depends on the depth of the section. So there are provisions to include, some of those are there. But the simplest form, even the simplest form has changed, but we'll use ignoring the effects of reinforcement ratio. The reinforcements provide additional shear strength. So like if you have in slabs, of course you don't have shear stirrups or you don't have the dowel action. So ignoring those actions, and for our course purposes this is fine. You probably get another 20-30% more if you include the shear due to the other actions, but let's keep it simple. Width multiplied by the depth. So 2 square root of 4,400, this should be in PSI, that's one of the requirements. So comes to 9.95 kips. You do get more, but so this one is lesser of the two. That's so Rm is equal to 9.44 kips. Now, the other thing is also, I had mentioned that, let me mention Rm. This is Vc. This is interesting to see. Now, if you have this is Rm by 2, this is Rm by 2, this is the span 13 feet. If you see the capacity, that's the shear capacity somewhere here, but that VC is Rm by 2. The actual Rm is multiplied by 2. So, Rm by 2 equal to Vc. So, therefore, the shear capacity is actually 19.5. So, 9.95 multiplied by 2, 19.9 kips. So, the flexure capacity is anyway half. Then the longer time is taken in you rarely put stirrups in slabs. It's just impractical to do it. Unless you specify it, then they will put it. But it's rarely put. But if you feel like it, you need to put it here, it's up to you to recommend it. Yeah. So, the member stiffness have you done we've all done crack moment of inertia calculations, yes or no? I know mechanical engineering you may not have, but concrete you've done crack moment of inertia calculations? It's been a while. There are several answers. Yes? Huh? No, the crack moment of inertia. Okay, I think I'll go through it. If we go a little longer, let me go through it anyway. What do you think? Go over it? Okay. So, simply supported beam, KE is 384 E sub C, I sub E divided by 5L cubed. So, first we calculate the effective moment of inertia. So, part of it, find the ratio of the modular ratio, which is ES divided by EC, and EC in the US there are more complicated equations. The simplest one is 5700 FC prime. This is in PSI units. So, you should be 57,000 multiplied by, here you can take 4000 itself, it is not going to make much of a difference, PSI, and E sub S is 29 into 10 power 6 PSI. So, substituting in all of this, you get N is approximately 8. N can vary from 4 to 8 or 6 to 8 depending on the strength of concrete, steel, so on and so forth. So, that is the modular ratio. Now, the second step is I am showing you all the details. So, calculate the neutral axis depth. This is elastic behavior. So, based on elastic behavior, but we are going to apply to plastic scenarios. So, so this is your slab, this is 8 inches, this is your neutral axis, depth C, this is steel reinforcement at 6.25, and remember we are considering 1 foot of it. So the area of steel is 0.4 square inches. So we use the moment of area concept, and we say A1 multiplied by C equal to, so if this is C, this is C by 2. So A1 multiplied by C by 2 is equal to, the modular ratio is used, NAST multiplied by this distance is D minus C by 2. So we are taking moment of area about this point. So here it is, A1 is 12 inches multiplied by C, so that's 12, this area, the green area. 12 times C multiplied by C by 2 is 8 times, it's like D is 6.25 minus C by 2. So I'll skip this step, solve the quadratic equation, and you get C is equal to 1.58 inches. Then the third step is apply the parallel axis theorem. What's that? Why am I not using what? So this is elastic behavior. When you do deflections, right, you're still calculating. Remember, your building is 100% loaded with full load, it's still elastic behavior. So deflection calculations are all done real deflections. Okay. So when you do the parallel axis theorem, in this case, you're applying say 1 feet, 12 inches. So now this is the concrete part of it, 1.58. This is sort of the steel part of it. Imagine this is a box with area N times AS, and this is my neutral axis. So from here to here it is C by 2, this is D minus C by 2. So the overall moment of inertia about the neutral axis can be broken down into two parts, I bar of C plus, so this is D1, and I'm going to not spend too much time. If you have questions, ask me later. A1, because I want to put time, I want to get these numbers through for completeness, plus for steel, this is for concrete, steel is I bar can be taken to be 0, plus NAS times D minus C square. So this is 12 inches multiplied by C cubed by 12 plus 12 times C multiplied by C by 2 square plus 0 plus 8 times 0.4 times 6.25, and we know all these numbers comes to 86. So again, if you have any questions, don't hesitate to ask. One thing is, but we'll just hold on to this part later. Now also this is the neutral axis, this is the cracked neutral axis, moment of inertia. The gross I sub g is simply BH cubed by 12. So this is 12 times, the depth is 8 cubed divided by 12. So this is 512, and you can say the I effective. There are other methodologies. The I cracked has to be less than that. So it depends. If you take I effective to be now 300, now you might come back later and say, no, the blast is going to completely crack it up 100%. Can I use 84? I mean, it's a big difference, right? 84 versus 312. It's really up to you. You can try it out and see. Nobody is going to question that. You get much higher, but those are some decisions you have to make, practical decisions. Can IE be equal to 84 inches square, inches per 4? Perhaps yes. You can try out. What I would recommend in this case is, if I were doing it, I would check both, check my deflections, go through the procedure twice, come up with my own judgment. So, therefore, now EC, as I had mentioned, is 57,000 square root of 4,000 psi. Now divided by 1,000 to get KSI. So in your own units, you can calculate E sub C, E of concrete. So we now calculate the first value. This is 384 E divided by 5 L cubed. So which is 384 multiplied by 3605 KSI multiplied by 300 inches per 4. It's going to make a big difference what K you use. 5 times L is 13 feet. So comes to, so you'd see that in non-lin you can, if IE equal to 84 inches per 4, that is, it reduces your KE to what is 21.8 multiplied by 84 by 300. How much is this? Roughly a fourth, right? About 6, no, 1/4, 5 something, right? 6.1. So big difference. Then I don't know which step we are in, but calculate static and dynamic deflection. The static deflection is P naught by KE, which is 19.656 kips divided by 21.8 kips. So the difference would come somewhere here, 0.9 inches. Then this is the second part, is find the natural time period. So for this, M is concrete multiplied by the volume divided by G. So for us it is 150 pounds per cubic foot. B was 12 inches, height is 13 feet, thickness was 8 inches, and all of these are divided by 12 for consistency. That's 13 feet. So 12 inches, 8 inches converted to feet, and G is 386. So comes to 3.367. Now here we use the equivalent mass. So here you can use K plastic plus K elastic by 2, and I had shown that equivalent mass, not this one, but equivalent mass for a this is propped cantilever, we are simply supported. So you can use these to get, I'll read it for you. This is, if you see, mass factor is between these two. Load mass factor is 0.78 and 0.66 here. So this is KLM elastic. There are several factors, so use KLM plastic, that Km by KL divided by 2. So this is at 0.76 plus 0.68, I believe. So the effective mass is KLM multiplied by M. Here's your KLM, and M comes to 2.4. Or the natural time period is 2 pi by multiplied by ME divided by K, comes to 2 pi, we are almost there, 2.4 divided by, now this is in pounds, so let's convert this to 21,000. If you have time over this, the break, lunch break, you can try for the lower value and see what you get, and then we can discuss, or we can do that as a tutorial part during the break, after the lunch, after, and when we meet again. So the response type is Td by Tn is 22 by 66 milliseconds, is, so it's closer to impulse, it could still be in the dynamic region. And then Rm by Fo, Rm was 9.44 kips, F naught is 19.5 kips, so this was 0.48. And if we insert this chart, which this one, right? Let me see if I can copy it. Oh, cannot copy from, okay, I need to import that, or we can, oh wait, why is it, wait okay, the same scroll bar does both functions. So if we come here, what was our Td by Tn? So 0.2, 0.3, 0.3. So roughly 0.33, and Rm by F naught is how much? 0.5. So 0.5 is 345. So this curve. So this curve. So this curve here, here we are getting the value is 133. So you can do a little more. I think I'm not very accurate. You can do that. So from the elasto spectrum, delta dynamic static equal to 3. So delta is times 0.9, right? What? I know I'm cutting into your lunch time, but it's almost there. Couple of checks. We do the ductility is delta max by delta dynamic, of course. Sorry. So here calculating the strength using it as delta E. So this is, and support rotation we can check against the LOP. I'll bring that tomorrow. Back, but theta is equal to tan inverse 2 theta is delta by L over 2, tan inverse 2 delta by L dynamic, and L is by L. So 2 times 2.7 inches divided by 13 times 12. I don't know how much this is. This is roughly 1 point something degrees. I think this afternoon, maybe we can, it's already 1 o'clock. I'll see if we can demonstrate using non-lin the same thing, right? We can, or we can do it tomorrow, whichever. Oh, it is? Okay. Yeah, we can show this and then you can do as part of today's tutorial also. How much is this? What do you get? 1 point? So we'll look at it this afternoon and work. Sorry if we went a little over. So the next 2 days, I think this will be more, this is all analysis. We'll focus on analysis, design also in the next couple of days before we start moving into winding up with some advanced other topics, advanced analysis, progressive collapse and things like that. All right, thank you for your patience, everybody. Nobody complained, we went 15 minutes over.